Morning. Now we'll study about beams of uniform strength. Now so far we have discussed about beams of uniform cross section throughout the span, isn't it? We have taken a beam and we have taken this cross section of beam as either rectangular cross section or I section, or we have taken channel section, or we can take T section. So here the section will be uniform throughout the length of the beam. Throughout the length of the beam, the section will be uniform, either rectangular or I section, channel section or a T section, or sometimes maybe a circular section. So for various types of loading, we know that the bending moment changes. The bending moment will not be uniform throughout. It will be maximum at the center for a centrally concentrated load, and it will increase and become zero at the supports. So the bending moment varies from section to section. Each section we can see the bending moment varies. But our selection of cross section is based on the maximum stressed, and hence it is some point we can see it is underutilized. Now we have studied that while designing a beam, we will select the selection, or we will select the cross-sectional dimensions of the beam based on the maximum bending moment. So here you can see the bending moment is maximum only at the center of this span. At all other sections, the material of the beam is understressed and hence it is underutilized. So it is possible to use smaller cross sections wherever the bending moment is less. For example, we can see the bending moment reduces from maximum to zero at the supports. So it is possible to use smaller cross section where the bending moment is less. So a beam in which maximum bending stress at all cross section is same is called the beam of uniform strength. So if we are selecting a beam with the maximum bending stress at all cross section is the same. Okay, so bending stress at all the cross section will be same. Since we are changing, we can ensure this by changing the depth or breadth of the beam. Okay, so you know the value of equation for bending moment as m equal to f into z. So f will be constant. So in order to make this m equal for all the sections, we can change the value of z. How can we change the value of z? By changing breadth or depth in the case of a rectangular cross section. So this type of beam is known as a beam of uniform strength. It is a beam in which the maximum bending stress at all cross section is the same, and this is an ideal beam from economical consideration. So how can you define a beam of uniform strength? If a beam is designed in such a way that every extreme fiber along the span is loaded to its maximum stress, then it is known as a beam of uniform strength. Now this you know that whenever a beam is loaded in practical situation, the loading will not be same. The loading will differ for different sections. So this beam of uniform strength is applicable only for a given type of loading. For example, in the case of the spring of a vehicle. So in the case of buildings, this is not possible. The loading will be different for different sections. So a beam of uniform strength can be provided only for a given type of loading. So what is a beam of uniform strength? A beam designed in such a way that every extreme fiber along the span is loaded to its maximum stress, then it is known as beam of uniform strength. Okay. So if you have a beam like this, and you can see the bending moment is maximum at the center, and if you draw the cross section of the beam, if this is the cross section of the center, we can say that this at the center both the extreme fibers will be subjected to maximum stress. Now all other cross sections, the cross section at some other section, like let this be x1. So if you take the cross section of this section x1, the bending stress will not reach the maximum value, since the bending moment is lesser than the maximum bending moment at this section x1. So the fibers will be underutilized. So how can you ensure the maximum utilization of the fibers? We can change the value of Z in order to make M constant. So M is proportional to Z because F is a constant value. So how can you make this value of Z changing? By changing B or D. So by changing the breadth and depth, we can ensure that for the whole span of the beam, all the extreme fibers is loaded to its maximum stress. So the design philosophy for beam of uniform strength is M is equal to F into Z, in which F is a constant. So M is proportional to Z if F is same at every cross section. So if we know M, we can get expression for Z, that is the section modulus. So the required section modulus at a section is obtained by changing either width or depth or both width and depth. Okay. So now we'll see, for example, if you have a beam like this, we can ensure the maximum stress at every cross section along the span by either changing the depth of the beam, that is by providing maximum depth at the center of the span. So actually this is the cross section of the beam. So in usual case we will provide the cross section as rectangular, but for a beam of uniform strength you can change the breadth or depth of the beam. So here you can see the depth is maximum at the center, so and it increases to 0 at the supports. We know that at the supports the bending moment is 0. Thus we can ensure that all the fibers will be subjected to maximum bending stress. Okay. So this is the plan of the beam. So another way is we can this is the elevation, and this is the plan. So here the width is same but the depth changes. So here the in the plan the width changes, the depth remains constant. So these are the different ways. So it will be clear when you do this problem. So the question is, determine the cross section of a rectangular beam of uniform strength for a simply supported beam of 6 meter span subjected to a central concentrated load of 20 kN by keeping the depth of 300 mm throughout. Second case is by keeping the width of 200 mm throughout, and it can take the permissible stress as 8 Newton per millimeter square. So in this question you have to find out the cross section of a rectangular beam. We have to make a beam of uniform strength. The beam is simply supported, subjected to a centrally concentrated load of 20 kN. 6 meter is the span of the beam. First case is we have to keep the depth of the beam 300 mm throughout. Depth is constant. Okay. So this is a beam. You have a centrally concentrated load 20 kN. So this load will be equally shared by the supports. So we can write the support reaction as 20 by 2. Now we can write the bending moment at this section XX at a distance small x from the left support. You consider a section XX at a distance small x from the left support. Now you write the bending moment at this section. Bending moment is equal to, if W is the load 20 kN, W by 2 into X. Now what is the bending formula? M equal to Fz. Now let us substitute that here. We have the bending formula M equal to Fz. So we have got M equal to W by 2 into X at the section into Fz. So let us take if B as the width. B is width and D is the depth. Then we can write Z equal to BD square by 6. So let us substitute in this equation. W by 2 into X is equal to F into BD square by 6. So we can write that is 1 by 6 BD square is equal to 1 by 6 BD square is equal to W by 2 into X into F. Or we can write BD square is equal to 3WX. So it is W by 2 into X divided by F. 3WX by F. Now case 1 is beam of uniform strength of constant depth. If depth is constant, then breadth is to be varied. Now from this equation we will get the equation for breadth B is equal to 3WX divided by F into D square. Now we can see that here breadth varies linearly with X, that is, this is a linear variation. So we can find the value of breadth at X equal to 0. When X equal to 0, what is the value of breadth? When X equal to 0, you will get breadth is equal to 0. When X equal to L by 2, what is the breadth? Breadth is equal to 3WL divided by 2FD square. Now we can substitute the value of W and L into 10 cube kilonewton into 6000 millimeter divided by 2 into F is 8 Newton per millimeter square. Depth square is 300 square, which is equal to 250 millimeter. So here we have kept the depth constant and the breadth is varied. So how can you draw the figure? If you draw the elevation, the depth remains constant. So this is the elevation. So what is the value? Depth is equal to 300 millimeter and the span of the beam is 6 meter. Now if you draw the plan of this beam, you can see the breadth is varying. The breadth varying means we have to keep it like this. So breadth is maximum at the center of the span. So this is equal to 250 millimeter. So this is the plan of this beam. Okay. Now the second case is beam with constant width of 200 mm. So here the breadth is varying. That is, the depth is varying while the width is kept constant as 200 mm. So we have to find out what is the value of the varying quantity, that is depth. From the above equation we will get depth is equal to root of 3WX by FB. So we can see depth varies with root of X. So we can find out what is the value of depth when X equal to 0. When X equal to 0, the depth is equal to 0, and when X equal to L by 2, depth is equal to root of 3W by FD into root of L by 2. So when you substitute the values, root of 3 into 20 into 10 raised to 3 divided by 8 is F 8 Newton per millimeter square. Depth, it is given that we have to keep it constant 200 mm into root of 6 into 10 raised to 3 by 2. So you will get the value as 335.41 millimeter. Okay. So we have got the equation of depth varies with the root of x, that is x raised to 1 by 2. So the variation of depth is parabolic. So the depth of the beam is maximum at the center, which is we have got 335.41, and minimum at the supports. The plan remains constant. Plan is same because the width is constant, that is 200 mm. Here the depth is varying. Okay, thank you.